Hi there. This is a screencast for anyone in Biology 1134 who was unable to attend lab this week because of an excused absence. That will take you through everything that we did in lab and allow you to make up the lab experience and get the assignments to your lab instructor. So this week is about an introduction to statistics. You are required over the course of this lab to analyze data, and we want to make sure that you know how to analyze data correctly rather than incorrectly, and so we want to take some time at the beginning of the semester to go through what this is going to be like. So the types of data we're going to analyze in this lab are two types. One type is data about distributions. Just to illustrate what we mean by this, think about M&Ms. Mars Candies makes M&Ms. They have two different factories that produce M&Ms, and they produce different ratios of colors at the two factories. Hackettstown has this ratio of colors, and Cleveland, Tennessee has this ratio of colors. And let's say that you go to the store and you buy a bag of M&Ms off the shelf at your grocer and count the number of M&Ms of different colors. You should be able to use a chi-square test to test the ratio of colors in your bag versus the expected ratios from Hackettstown and Cleveland, Tennessee, and determine which factory your M&Ms were produced at. And so this is the kind of data that this is the kind of analysis we will look at when we are looking at genetic data. What do we see in genetic genotypes relative to what we expect on the basis of a theory, Hardy-Weinberg equilibrium. So we'll talk about these types of analyses next week when you'll actually be using them. The other type of data we will analyze is data about means or averages of samples. Specifically, we're going to examine differences in bite forces among herbivores, carnivores, and omnivores, and we're also going to analyze differences in growth rates among bacterial populations growing at different temperatures. In both these cases, we're comparing two or more means, so the appropriate method of analyzing these data is with an analysis of variance. In the past, what we've done is we've relied on the fact that most people have conducted a t-test probably at some point, and we did multiple t-tests, but that's actually not the appropriate way of going about it. ANOVA is used when we want to compare means among three or more samples. It's more useful than multiple t-tests because it controls for type 1 error rate. Take a minute to think about what type 1 error rate might be. So just pause the video here, think about it, look it up maybe if you don't know it, if you've not been exposed to this. So pause the video, figure out what type 1 error rate is. So type 1 error rate is the probability of concluding that two means are different when they're actually not, if we're talking about an analysis of variance. So it's saying two things are different when they're not. This is referred to as an error because you conclude that something's different when it's not. This is different but related to type 2 error rate, which is the probability of concluding that two or more means are not different when they actually are different. So this is sometimes easier to think about in terms of an example, but in either case, you'll never know when you make one error or the other. These are just probabilities of making errors. If you conduct 100 experiments in your career as a scientist and you test all of them at a type 1 error rate of 0.05, meaning a 5%, you have a 5% chance of concluding that things are different when they're not, and all 100 of those experiments showed a significant result, then chances are 5 of those experiments are not reaching the correct conclusion. So, but you'll never know which one of those experiments it is. Once again, these are just probabilities of making errors. P is related to alpha in that it's the observed type 1 error rate based on your data. You generally don't want to conclude two means are different unless your observed type 1 error rate is smaller than the type 1 error rate that you would find objectionable to accept. So once again, easiest to think about this in terms of an example. Generally, we use 0.05 in biology. But imagine that you have a cancer drug that we think cures glioblastoma. Glioblastoma is a deadly type of brain cancer. We think it works, but it causes liver damage such that you might be cancer-free, but now you need a liver transplant. You want to know if the drug really works, so do you want to compare the control group to the people who got the drug at an alpha level of 0.05? You want to make the mistake of concluding that the drug works when it doesn't, do you want to make that mistake 5% of the time? Probably not. You might want to lower your alpha level to 0.01 or 0.001 because you want to be really, really sure that it works. Now, the problem with changing your alpha level, and that's the thing that you need to realize about alpha level, your type 1 error rate that you're going to use to make decisions about whether there is a difference between the control group in this case and the group that got the drug, that type 1 error rate is under your control. You're the one who determines how small of a type 1 error rate you need to observe to make the conclusion that the thing actually works. But as you make the type 1 error rate smaller and smaller, it makes it more and more difficult for your observed p-value to be low enough so that you might think that the drugs work. And so you end up thinking that some drugs don't work when they actually do. So you have to think about type 1 error rate and type 2 error rate, because as you run away from committing type 1 error, you run into the awaiting arms of type 2 error. And so think about these two in concert with one another, because as you avoid one type of error, you're likely to make the other type of error more often. We tend to stress type 1 error rates in science, but it's dangerous to not think about the implications of what the effect of type 1 error rate is on type 2 error. Generally, when we're asking questions about the equality of two means, we ask, could these two means have been drawn from the same underlying statistical population, or were they drawn from two different populations? So the first thing we need to address is, what exactly is a statistical population? A statistical population is the set of all observations about which we want to draw an inference. Go back to think about lecture. When the coot study people were doing their study, their population of interest, their statistical population, was all broods of baby coots everywhere. Now clearly you can't access all coot broods everywhere, so the researchers selected a random sample of coot broods, and they hope that those samples tell us something reliable about the entirety of all coot broods everywhere. So how can we reasonably expect to sample from a population and have that inform us about the statistical population? Well, we rely on two things that allow us to do this. The first of these is the central limit theorem, and the second of these is the empirical rule. So these are two crucial ideas that you need to understand when thinking about statistics. So the central limit theorem basically says that if you take a sample from a population, calculate that mean of that sample, save that mean, return those observations back to the population, resample that population over and over again, saving each of those means each time, the distribution of sample means that comes out of that sampling process will be approximately normally distributed regardless of the shape of the underlying distribution of the population. It could be a normal distribution that you're drawing those samples from. It could be a bimodal distribution. It could be a skewed distribution. It could be an exponential distribution. Any shape doesn't matter. If you do this, you will get an approximately normally distributed distribution of sample means. The other thing is that the average of the distribution of sample means will be a very close approximation of the population mean, if you're interested in estimating the population mean, although most people are never interested in estimating the population mean. So imagine that we have a bunch of card decks in a card feeder like they have at a casino, where they have like 7 decks in this one card feeder. We draw 2 cards out and note their values. Ace, 1, 2, etc., etc. So an ace is 1, jacks, queens, and kings are 11, 12, and 13. So we can average their values, and then we can store that average. We do this 50 times and look at the distribution, and the results are 2 slides from this one. But before we get to those results, what type of distribution is this? What type of distribution is a deck of cards? In addition, what do you expect the population mean to be of this multi-deck of cards? Pause the video, answer these 2 questions before proceeding on. So this is a uniform distribution. It's uniform because there are 4 versions of each face value card. There's 4 aces, there's 4 twos, there's 4 threes, there's 4 fours, there's 4 kings. Based on the central limit theorem, what do you expect the distribution of sample means of 2 cards drawn 50 times to look like? Once again, pause the video for a minute, think about this, answer this question before moving on. Well, based on the central limit theorem, you should expect the distribution of the sample means of 2 cards drawn to be an approximately normal distribution. So let's see what the data look like. I programmed R to basically do a simulation where it draws 2 cards 50 times from a deck of cards, 50 times with replacement. And this is what it looks like. And it doesn't look particularly normal. And the reason it doesn't look particularly normal is because it's only based on 2 cards, which is a small sample relative to the size of the population we're estimating, which is 52 cards. And these 2 cards are drawn only 50 times. Let me interpret for you what this graph is. The red line represents the mean of the sample means, of the distribution of sample means. In this case, it's 7.4. The blue lines represent 1 standard deviation to either side of that mean, and the black lines represent 1.96 standard deviations from the mean, both above the mean and below the mean. And this is where the empirical rule comes in. We can basically estimate what the normal curve would look like based on where the mean is located and the spread of the distribution of sample means. So looking at the average value and the spread of the values, we can project what an expected normal curve would look like. And under that normal curve, we would expect 95% of the sample means to occur between 1.96 standard deviations away from the mean. And so 68% of the distribution is within 1 standard deviation, 95% of the distribution is between 2 standard deviations, 99.7% of the data is between 3 standard deviations. So when we calculate standard deviations for a distribution of sample means, we're going to use the formula for the standard error of the mean. So once again, this is a distribution of sample means, and so we're going to use the standard error of the mean to estimate this spread. And the estimate of the population mean in this case is 7.4. So that's not a particularly great looking distribution. So what happens when we draw the 5 cards 50 times? Well, the distribution still doesn't look terribly normal. This has big gaps in it, and it's not really normal looking. This is an expected normal distribution, assuming a mean of 7.02 and the spread of the data. And once again, I've shown you where the mean is, where 1 standard deviation is to either side of the mean is, and where 1.96 standard deviations to either side of the mean are. You'll notice that here the population mean estimate is actually closer to 7, which is the expected, but it's still not quite there, but it's very, very close, even with only 5 cards. So 5 cards is doing better than 2 cards, but another problem with getting a shape of this distribution is we're maybe not drawing cards enough times. So let's go back to drawing 2 cards, but now we're going to draw 2 cards 1,000 times. So here's the distribution for 2 cards 1,000 times. You can see this is beginning to look more normal. This is once again an estimated normal curve based on the mean and the spread of the data. And in this case, we can also see the mean, 1 standard deviation, and 1.96 standard deviations. Now, as we go through the next slides, we're going to basically go from 2 cards to 5 cards to 10 cards to 20 cards to 30 cards drawn 1,000 times. I want you to pay attention to how the shape of the distribution changes and how the breadth of the distribution of sample means changes. Keep in mind that with only 2 cards drawn 1,000 times, we're very close to the population mean when we calculate the mean of the distribution of sample means. So here's 2 cards drawn 1,000 times, 5 cards drawn 1,000 times, 10 cards drawn 1,000 times, 20 cards drawn 1,000 times, and 30 cards drawn 1,000 times. What you should notice is that as sample size increases, the breadth of the distribution of sample means becomes more and more narrow. So if we were to gather an additional sample of 30 cards from the same population, we should expect the mean of that population to be within 1.96 standard deviations of the mean of the distribution of sample means. So we would expect it to be somewhere in the range of slightly below 6 to slightly above 8. This narrow band is where we would expect any sample mean that was drawn from the same population, we would expect it to fall in there. It doesn't mean that it can't fall outside of that range. It just means that we would expect the vast majority of them, 95% of them, to be in this range. If we drew a sample of 30 cards from the sample population, and that mean was outside the black vertical lines, we would have reason to expect that the 30 cards we drew were actually from a card deck that is different from the card decks we have been drawing from to create this distribution of sample means. And that's basically how comparing means works. It's a question of inclusion. Does a new mean get included inside the 95% confidence interval of this distribution of sample means, or does it fall outside of that 95% confidence interval? And this is where 95% confidence interval comes from, the fact that 95% of the expected sample means should fall within this range. So this is what happens as you go from only drawing 2 samples to drawing 30 cards in a sample. You go from poor match of a distribution to a better match of a distribution. So when we combine the central limit theorem and the empirical rule, this is what makes statistical comparisons possible. Some people think we can tell if two means are different based on how much their distributions overlap, but a better way of doing this intuitively is ask, could the mean of one sample have come from the distribution of the other sample, and from the distribution of sample means of the other sample? So we can make these types of decisions for multiple means simultaneously using the analysis of variance, but we need to go through some calculations that help us get there. So it's going to take us several slides to go through how the ANOVA works, but before we get there, we need to do some simpler calculations. Now, you're going to see equations throughout the rest of this presentation, but know that if you understand how an ANOVA works, you don't really need those equations, and if you don't understand how it works, no equation is probably going to help you. So let's look at an example. A plant biologist wants to know the effect of different types of water on the growth of plants. He knows that plants need sugar as a source of energy, so he decides to add a 2% solution of sugar to the water and compare that to control, that is pure water. He also knows that glucose, a simple sugar, is what they produce through photosynthesis, but they also produce fructose and sucrose, and so he wants to test a variety of different sugars, and so he decides to create 4 experimental watering regimes. There's a 2% solution of glucose, a 2% solution of fructose, a 1% to 1% ratio of glucose to fructose, because glucose and fructose are the simple sugars that are bonded together in sucrose, so he also has a 2% solution of sucrose. He waters these plants and grows them for a period of time, and then measures how much they grow. This is what he refers to as the growth increment, and then these are what the data look like. Now, look at the data and just ask yourself for a minute, what do you think the effect of adding sugar water to the plants is on plant growth? So pause the video and look at the data for a minute and kind of make your own gut conclusion on what the effect of adding sugar water to plants is. Well, this isn't the only way to look at the data. We can actually look at the data in graphical form. So next slide. Here is the range of the data that we have. We have control and the 4 treatments, and we can actually just plot the data for each of these treatments on the number line, where each dot refers to one of the samples or one of the treatments. And in all these cases, there are 10 observations, so there should be 10 dots. They're stacked on top of one another whenever we have multiple observations of the same growth increment. Now look at the data. What do you think is the effect of adding sugar water on plant growth? Pause, take a minute to answer that question. If we want to compare means, we need to do some well, let's go back. you basically should conclude that maybe the control is higher than sucrose, maybe sucrose is higher than the rest of these. That would be an appropriate answer to this question. So if we want to compare means, we need to be able to calculate the mean and some measure of the spread of the data around the mean. And the spread of the data around the mean that we're going to want to calculate is the standard error of the mean. The standard error of the mean is what relates the sample that you've taken back to this distribution of sample means. And so that's what we're shooting for. As we saw in previous slides, the larger the sample we have, the better we can estimate the population mean. So we're also going to multiply the standard error of the mean by a multiplier called the t-statistic, which either broadens the interval around the mean if we have really small samples, or shrinks the interval around the mean for larger samples. And this once again helps us relate it back to the distribution of sample means, which is what we saw in all those distributions earlier. Essentially, the larger our sample is, the smaller our confidence interval can be, because we know more about where the population mean is located. So let's calculate the mean and the 95% confidence interval of the mean for the control data. Once again, just to remind you, here are the data: 75, 67, 70, 75, 65, 71, 67, 67, 76, and 68. So 10 plants and their growth increments under pure water. So we have 10 values. So to calculate the mean, we use the formula. The mean is equal to the sum of all of the values divided by the number of values that you have. In this case, the I and the J, so don't let the formula scare you. The sigma just means add things up, and we're adding from J equals 1 to n, which is the number of values that we have. J is 1 through 10, so we have 10 values within the ith treatment. So the ith treatment in this case is the control treatment, but we have other treatments. So these letters that are subscripts just help us keep track of which treatment we're in, given by I, and which value within that treatment it is that we're working with at any given moment. So what it looks like is this: you add all those numbers up, you divide by the number of values that you have, and you get a mean of 70.1. So you know how to do an arithmetic average. That's all the sample mean is. So the next step on our path to calculating standard error is to calculate the variance. Variance is a simple measure of the spread of the data around the sample mean. For the control data, it might look like this. So once again, here is our number line with the data for the control. Our sample mean is 70.1, so the variance is made up of the distance between the mean and that observation, the mean and this observation, but because there are 3 of them, we have to do that 3 times. The mean in this observation, the mean in that observation, the mean in that observation, but that's there 2 times, and the mean of that observation. Now, when we add all of this up, they're going to sum to 0, because the mean is in the middle of the data set, and we have just as much weight in the data set to one side as we have to the other side. And as a result, this is going to all sum to 0. Well, that doesn't really get us anywhere, because we want to know what those magnitudes are. So we can square them, which converts them all to positive values, and then add them up. And so this is exactly what is referred to as the sums of squares. So anytime you hear that terminology, sums of squares, it's the squared deviations of the data from the sample mean. So we would take each of these distances, we would square it, and we would add it all up. We then divide the sums of squares by the degrees of freedom for the variance, which is 1 minus the sample size, and that will give you the variance. The reason that we reduce the degrees of freedom by 1 is because when we calculate the mean, we use all of the information that is in the data set to calculate the mean. And so it's divided by the total size of the data set. When we calculate the variance, we're using an estimate of the mean to give us an estimate of the variance. And so we have a little less confidence in the estimation of the variance, because it itself is estimated on an estimate. And so we reduce the amount of information that we have to 1 minus the sample size to account for that uncertainty. This is known as the mean squares within a sample, and it's a deviation divided by the degrees of freedom, in the same way that with the sample mean, the sample mean was adding up all the values divided by the sample size. The variance is adding up all of the sum squares divided by the sample size minus 1. And so we refer to this as a mean square. It's analogous to a mean. And so this is what it looks like. We have each value minus the mean squared. Each value minus the mean squared, but we do this 3 times because there are 3 of them. Each value minus the mean, and over here we're doing this 2 times because there are 2 of these. And in this case, the variance is 15.8778. So if you calculated this out yourself, that's what you would get. And I advise you to calculate this yourself. Note that the numerator is the sums of squares, so if you ever need to know the sums of squares, you can just multiply the sample variance by the degrees of freedom, and it will return to you the numerator here, which is the sums of squares. So take this equation up here at the top, multiply times n minus 1 and n minus 1, and you'll get the sums of squares. Now don't let this equation get the best of you again. It's really just saying take the individual values, subtract the treatment mean from those values, square those differences, add them all up, and divide by the sample size. So I've drawn some arrows here. This is the data point, this is the mean, and this is the degrees of freedom. And then you just repeat that for all of the values within your sample. And this is the sums of squares within, because this is looking at within treatment variation within control. Then we need to calculate the standard deviation, which is just the square root of the variance. And once we have the standard deviation of 3.9847, we can calculate the standard error of the mean, which is the standard deviation divided by the square root of the sample size. And I've tried to come up over the years of a like intuitive way of thinking about why this is the equation for the standard error of the mean, and I failed at that. And so this is just one of those equations that you're going to need to remember or look up. But it's 1.2601 when we take the standard deviation and divide by the square root of 10. Now what we're going to do to calculate the confidence interval is we're going to basically take this measure of the standard error of the mean, and we're going to multiply it times a multiplier that we get from the t-table. And this is the thing that once again relates how much confidence we have in our estimate of the population mean based on our sample size. So we're going to use an alpha of 0.05 because we want to construct a 95% confidence interval. And once again, the degrees of freedom is 1 minus the sample size. And we're going to add that to the mean and subtract it from the mean to get the 95% confidence interval. Where do we get this t-statistic? Well, we find it in any t-table. So here's a full t-table from a statistical text, and I've zeroed in on the section that we need because our within sample variance has a degree of freedom of 9 values. And so we're going to go to the 0.05 column, we're going to go to 9 degrees of freedom, and we'll see that our t-statistic is 2.262. And so we're going to basically create an equation where we have 70.1 is the mean, and we add to that 2.262 times 1.2601, and we subtract from 70.1 2.262 times 1.261. This creates a confidence interval that extends from 67.25 up to 72.95. So what does that confidence interval mean? There are 2 common ways in which we interpret the confidence interval. One is that there's a 95% probability that the population mean lies within this range. But that's actually the less useful version of interpreting this. The second version, the more useful version, is any sample mean generated from the same population as this mean has a 95% probability of falling within this range. The second of these is the interpretation that we use for comparing means. Thus, testing whether 2 means are different from one another is a question of inclusion. Is the mean of one sample included in the 95% confidence interval of another mean? do the calculations. So I'm going to give you the data set here on the next slide. Oh, if you were in class, you would have done this within your group, one person working on each treatment. So what I want you to do is on the next slide, pause the video and then basically work on, doing 2% glucose. Calculate the mean, the variance, the standard deviation, the standard error, the mean, and the 95% confidence interval for one of these treatments. Not the control, we've already done the control. So pause, do that, and then once you've done that, restart the video. So hopefully you've now calculated the mean, standard deviation, or mean variance, standard deviation, standard error, and 95% confidence interval for one of these treatments, and here's what it should look like. So we have the means right here, then we have the variances, standard deviation, standard error, the t-statistic, the width of the confidence interval above and below, and then the upper and lower limit to the confidence interval. So if we go back to our drawing, our figure, we can now plot the 95% confidence intervals on the figure. This is what it looks like for the control, glucose added, fructose, glucose and fructose, and sucrose. And now it's really easy to see which things are different from which other things because we have these confidence intervals that are drawn. And it appears that control is different from sucrose, sucrose is different from all of these, and control is different from all of these as well. And so these confidence intervals are all narrower than the range of data in the sample because this isn't trying, the 95% confidence interval doesn't tell you about the sample. The 95% confidence interval tells you about the distribution of sample means. And because we have a sample size of 10, that's not a great sample size, but it's way better than a sample size of 2. And so, once again, as the sample size gets bigger, the confidence interval gets narrower because you have a better and better estimate of the mean. So getting back to ANOVA, the goal of ANOVA is to determine whether means are different, but the ANOVA goes about this by analyzing variances. The ANOVA asks, is there enough variance among the treatment means that we can say they're different given the variance within the treatments? So going back to the sugar water plant growth example, we have the means, and imagine that we have the distribution of sample means around that mean. Distribution of sample means here, distribution of sample means here, here, and here. The question is, are the differences among the means far enough apart, are the means far enough apart that this mean does not fall within the 95% confidence interval of this distribution of sample means? So that distribution of sample means is a function of variation within that sample. So is the variation between this mean and that mean big enough to be noticed given the amount of variation within this sample and the amount of variation within this sample? So it really is about comparisons of variation. In the case of the 3 simple sugar examples, those means are all relatively close together relative to the variation in the distribution of sample means. So we might conclude that those are not different from one another, but we notice that sucrose is quite a ways away from the simple sugars, and sucrose is quite a ways away from the control, relative once again to the variation of the distribution of sample means of each of those treatments. And so that difference is not obscured by the within sample variation. So how does ANOVA quantify treatment variation, within treatment variation, and among treatment variation? Well, you already know how to quantify sample variation within treatments, right? Remind yourself briefly what that is. You subtract the sample mean from the data points, you square each of those differences, and you add them all up. In ANOVA, you then do that for every treatment that you have, and you add all of that up. This is the sums of squares. It's merely the numerator of the sample variance equation that we used earlier. In an ANOVA, we do this for every treatment, add them all up, and this gives us a cumulative sums of squares within samples. It's abbreviated sum squares within. To quantify among treatment variation, we just do kind of the same thing, but we begin with the grand mean, which is the average of all the values in the data set as if they were not partitioned out into treatments. For the plant growth data set, this is an average of all 50 values in the original table. Once you have the grand mean, you merely subtract that grand mean from each of the treatment means, square those differences. Once you've done that, you then have to multiply those square differences by the sample size. So there's a weighting, and then you add all those weighted square differences up. This is the sums of squares among treatments. So this is mathematically what the calculations look like. Now I realize that you just lost your mind seeing all of these symbols, but let's just break it down. The treatment means are found right here. And once again, it's just adding up all the values within the first treatment and then dividing by the number of observations in that treatment. We do that for all of these things. Now, the mean of those means is the grand mean, but in this case, the observations are the same in each category. In each category, there are 5 observations, and so we can just average the averages. But if these things were different sample sizes, you would actually have to weight each mean by sample size and then divide by the total sample size of the total data set. And it will give you the same answer as if you just added up all of the individual data points and divided by total sample size. The grand mean is once again just adding up all the values and then dividing by the total sum. So let's break it down. Add up all the data within a treatment, do that across all treatments, and then divide by the total sample size of the entire data set. That's all this equation means. So I'm going to give you little English interpretations of what the symbology means for all of the things that are in this table. Sums of squares within treatments is down here. I've blown it up for you here. Once again, it's just subtracting the mean from each data value within a treatment, squaring those differences, add those differences up within treatments, and then add them across all of the treatments. So that's the sums of squares within. You're basically doing it here, 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 and here, and then you're adding all of those up across all of the different treatments. Sums of squares among is here. In this case, we take the mean and subtract the grand mean from it. We square those differences. Then we weight the squared differences by the sample size. And this is the thing that you're most likely to forget to do. Be sure and always weight the squared differences by the sample size. And then you add all of those up across all of the treatments. So there should be 4 of them. And in this case, 5 of them in the plant data. Hopefully all the variation within the data set is explained by either variation within treatments or variation among treatments. So the sum squares total is due to the contribution of sum squares among treatments and sum squares within treatments. So you can calculate sum squares total this way, but you can also do a mathematical check on yourself because sum squares total is presumably the total amount of variation in the data set. There's another way of calculating this to check and see if your sum squares among and sum squares within is correct. The way to do that is to take the grand mean and subtract that from this value, square it. Subtract the grand mean from this value, square it. Grand mean from this value and square it. Grand mean from this value and square it. Grand mean from this value and square it. This minus grand mean, 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 this, all minus the grand mean and squared, this, all minus the grand mean and squared, and add all of those squared deviations of the individual data from the grand mean. When you add all of that up, that should be the sum squared total. So you can always mathematically check yourself. This is one of the other things that I like about statistics. It makes mathematical sense. So far, we've talked about using ANOVA to test for differences among treatment means, and we've calculated means, but we've used these means primarily to assess how individual data points vary from treatment means and how treatment means vary from the grand mean. This is why it's called an analysis of variance, not an analysis of means. The test statistic that you calculate is the ratio of the variance among the means divided by the variance within means. Remember, a variance is the sums of squares divided by the degrees of freedom. So when we go and look at a regular variance estimate, it's within a sample, so it's the value minus the mean, but it could also be a variance for among means if it's the mean minus the grand mean, squared divided by the degrees of freedom. So this is what the ANOVA table looks like, and this is what we're testing. A mean squared among, which is the variance among, and the mean squared within, which is the variance within. And we get that by dividing the sum squares within by the degrees of freedom for within, and the sum squares among by the degrees of freedom among. So that's that. And then we have the sum squares within divided by the mean square within, and that gives us, sum of squares within divided by the sample size, or the degrees of freedom within, and that gives us the mean square within. So going back here, let's talk about degrees of freedom. The degrees of freedom for among is the number of treatments, which is A minus 1. So the plant data has 5 treatments, so there would be 4 degrees of freedom here. The within sample sums of squares is the total sample size divided or minus the number of treatments. So that would be 50 values minus the 5 treatments, that's 45. 45 plus 4 degrees of freedom here should be 49. And the total degrees of freedom is the total sample minus 1. 50 values minus 1 is 49. So once again, you can check your degrees of freedom also. So you can look up critical values of the F statistic in an F table, like the next slide. You need to know the numerator and denominator degrees of freedom and the alpha level you want to test at. In our case, we're going to test an alpha level of 0.05. And the numerator degrees of freedom are the among treatment degrees of freedom, which is going to be 4 in this case, and the denominator is the within treatment, which is going to be 45. So if your calculated F statistic is higher than the one in the table, at least one pair of means is different, but it doesn't tell you which ones are different. It just tells you that there's a difference in there somewhere. The bigger the F is, the more differences you have, or the bigger the differences are. So we look in, once again, an F table from a statistics text, and what we find is that here is the numerator degrees of freedom 4, but the denominator degrees of freedom jumps from 40 to 60, and there's no 45 in between. As a result, this F table is useless to us. Fortunately, there are online calculators that will allow you to get the p-value of your calculated F statistic. A good one is here by a guy named Daniel Soper, who is brilliant and very generous with his time. So you can log on to here, you can give it the numerator and denominator degrees of freedom and your F statistic, and it will return a p-value. So what I want you to do now is analyze the plant growth data using the analysis of variance. Keep in mind that you've already calculated the variance for the treatments, so you should know a quick and easy way to get the sums of squares within for each treatment. You just multiply the sums of squares times the degrees of freedom, the variance times the degrees of freedom, and will return the sums of squares. You also know all the treatment means and sample size, so getting the grand mean should also be pretty easy. The work to be done is in calculating sum squares among. Don't forget to weight them by the sample size. Then construct the ANOVA table and go online to test the significance of your F test. So this is what it looks like, and you need to fill in the mean, the sample size, sum of squares within, sum squares among, sum squares total. You can take these things and add them across and put them in these boxes over here, and then get your sum squares within and among, transfer them to the ANOVA table down here, calculate the F statistic, and then report your p-value. So take a few minutes. Well, take a little while. It's going to take you a little while to do this. Pause the video, do this for each of these treatments, and then fill out the ANOVA table at the bottom. So pause, do that, then come back to the video. So this is what you should have found. These are the means. This is the means. The overall grand mean is 6194, which is just the sum of all of the values divided by 50, which is the sample size of all of the values added up. Sums of squares within for each treatment is found here. We add all those up to equal 245.5. Sums of squares among, once again, this is the weighted differences between the mean and the grand mean squared. Those add all up to 1,077. These values transfer down into the ANOVA table, and we see that there is a lot of variation that is accounted for by differences among treatments and very little variation that is found within treatments, which leads us to a very large F statistic, which ends up being very significant. When you went and tested this in Daniel Soper's website, you should have found that it reported a p-value of 0, which is basically, if you say that something is different in this data set, your odds of being wrong are virtually non-existent. And so it doesn't tell you what's different from what, but it tells you that at least 2 of these means are different, and that difference is relatively big. Or there are multiple means that are different with lesser degrees of difference among them. So now that you've done that for this worked out data, I want you to take a different data set, and this is what you'll turn into your lab TA. A mammal researcher wants to know the size of ticks on 4 hosts. She collects all the ticks off the host and measures their carapace width. The data are on the handout that you will receive in lab. They're also on the next page, so if you weren't in lab, you can just transcribe the data. Conduct an ANOVA on these data and produce a meaningful graphic complete with figure caption. And there is a video linked on the lab module for this week that shows you takes you to a video that I've created, shows you how to create a meaningful graphic and a figure caption, and then turn those 2 things into your instructor. Those are your 2 post-lab assignments. Since you're doing this as a makeup, this will be an individual and an individual assignment, but if you had been in lab, it would have been constructed by your group. You should have time to complete this before you leave lab, but you're not in lab, and your ANOVA will be graded on completeness and correctness. So here are the data. You'll notice that there are different sample sizes, so when you go to calculate sum squares among, be sure that you're weighting those squared deviations by the sample size of each of these things. I've given you some space here so that you can do the sum squares within calculations, and then there's space down here for the ANOVA table. And that's all you have to do this week.